Treated as last semester over the web, and you can get to the website through the department's list of courses. So I also emailed that out to you, so you might have received that email if you're registered for the course. All right, so this semester, as last, there will not be an official textbook, and we will be distributing lecture notes. Of the books that are listed here, I highly recommend the book by Sakurai for this material. It doesn't have everything that we're going to cover, but it has most things we're going to cover, and it's done very well. So if you have some cash to spare, I highly recommend picking up a copy of that. Okay. Other than that, so the course is organized similarly to as it was last semester. There's our TA. Welcome back, Obi. The grades will be based on homework and exams. There will not be a comprehensive final, but I intend this semester to give 3 midterms throughout the term. This semester, after some thought about it, they're going to be in-class exams. It's just impossible in the age of Google to give a take-home exam and just see it. It's all about can Google better and find things, and that's really not my testing. So we will schedule those as we did last year outside of class time, so that we have more time to do the exams. Let's see, what else in terms of the overall organization. So we do have a problem session. The problem session is scheduled at 10 o'clock till 11 o'clock or 11:30 on Fridays in room 5. I'll send you a message about that to remind you, and we will get started right away because there will be a homework assignment posted today. Get ourselves moving again for the semester. And so we will have a problem session. I tentatively scheduled my office hours as they were last semester, but I'll send a message around. And this semester we'll get more serious about we'll be having office hours as well, because I think it will be quite useful to have additional office hours for working on the homework. All right? All right, anybody have any questions about organization or any of the administrative aspects of the course? I think it's all pretty straightforward. All right, well then, let's get started. So let's see, what did I want to do here? Right, so I wanted to go back to this org chart that we had. Let me turn off the lights here for the moment. We won't be using this for much longer. But, in the first class of last semester, I kind of set out how I see, to some degree, what is quantum mechanics about? It's about a lot of different things. And there are different focuses that you will see in different courses, and different scientists are thinking about different pieces of this puzzle. Last semester, we really focused pretty much mostly here. We were setting up the basic foundations of the physical theory and understanding what quantum mechanics meant and how to use it and how to apply it. Okay? this semester is going to really focus much more in this area. It's really about the structure of matter. And in particular, what one might call normal matter, everyday matter, the matter of us, atoms and molecules, and pretty much mostly atoms, and maybe just a little touching on molecules. And we'll think about some of those applications as well in different areas. In thinking about the structure of matter, as we discussed last semester, a kind of unifying principle is the theory of symmetries. Symmetries are extremely important because they are the glue that allows us to connect physical degrees of freedom, the degrees of space and time, the world in which we live, with Hilbert space, the abstraction of quantum states and quantum observables. So it is through symmetries that we make that connection. And of particular importance within that is, one particular symmetry that's extremely important is rotation symmetry. Rotation symmetry is particularly important because it is the way in which we talk about the theory of vectors and tensors. And vectors and tensors are very important when we're starting to talk about the structure of matter and its interaction with electromagnetic fields. Normal matter, the forces which bind normal matter are electromagnetic. And so if we want to talk about electromagnetic interactions, we really have to think very carefully about the theory of vectors and tensors in quantum mechanics. So rotation symmetry, the theory, and as we know, the generator of rotation is angular momentum. The theory of angular momentum in quantum mechanics is also extremely important to make all those connections. Okay? And so the star of the show this semester is Eugene Wigner, so he got his picture on our website because Wigner was the person who really brought the theory of symmetries and groups firmly into quantum mechanics, and we'll be talking about that as we go. All right. So, with that motivation in mind, we're going to just jump right into it and kind of pick up where we were last semester. So, what we've just described right here is that rotations are generated by angular momentum. So we talked last semester, and as you know from your undergraduate studies, there are kind of two kinds of angular momentum we talk about. We have orbital angular momentum. Bless you. Right? Related to motion of particles, and we have spin angular momentum. Which cannot be understood as arising from the orbital motion of anything. Now, we talked about these kind of separately. Of course, we can also try to think about total angular momentum. So classically, if we have some, say an orbiting planet that's orbiting the sun, it has some angular momentum associated with that motion, and that body might itself be, in this case, it also orbital, but it could be spinning around its axis, so it might have some L and S, where S, of course, is also orbital, but it's the spinning particle, or the spinning Earth, right? And we would say, if we wanted to say, to properly treat the rotational motion of this body, we have to add angular momentum, right? And classically, angular momentum just adds as a vector. We have to be a little bit careful in quantum mechanics of how to think about this and what it means, because of course quantumly we can write down an operator which is the sum of the angular momentum operator vectors, but we have to think carefully about how we specify the states of the system corresponding to this total angular momentum, because of the fact that the different components of angular momentum don't commute. Okay? So what we want to study today to remind ourselves about is the theory of the addition of angular momentum in quantum mechanics. Which is extremely important. Now, that addition could be, as we described, examples are spin plus orbit for a given particle. Or we might think about total spin for a collection of particles. So for example, if we're thinking about matter, as we will, and we're talking about, say, helium, we have 2 electrons. We have to think about the total spin of the electrons, those atoms. Or we might be thinking about hydrogen with 1 proton and 1 electron. The proton has a spin, the electron has a spin, and important in all of radio astronomy is that total spin of the electron plus proton. Gives rise to the 20-centimeter line that is the lifeblood of some of you in this room. So understanding how to treat the total angular momentum of the system is extremely important in how we're going to study the structure of matter. Okay? Right. Okay. So how are we going to proceed? Well, so let's treat this generally. So let's say we have 2 angular momenta. Okay? So each of them is described, so there's a J1 and J2. So this J is the total angular momentum quantum number, this magnitude squared quantum number for two different degrees of freedom. It could be, J1 could say be L and J2 S in the spin orbit example. Or this could be spin of particle 1 and this could be spin of particle 2. All right? So the Hilbert space, as we've discussed, that in which this system lives is a tensor product of the two Hilbert spaces, one associated with angular momentum J1 and the other with angular momentum J2. So what is the dimension of this Hilbert space, H12? It's not, they don't add. First of all, what's the dimension of each? So the dimension of H1, that Hilbert space is what? If it has angular momentum J1. Here's going to get wider. So I have, say I have a spin 1/2. What's the dimension of the system?
2j plus 1.
Right, 2j plus 1. And in this case, 2j1 plus 1. And for H2, it's 2j2 plus 1. So what is the dimension of the tensor product space?
The product of those two.
The product of those two. Thank you. So that's the total dimension of the Hilbert space in which we're working. It's the product of those two dimensions. So for example, we had two spin 1/2 particles and we're looking at the total spin of the system, then this would be 2 times 2 or 4. All right? Okay, so we have, I'm going to define now, so there's an operator J1 acts on Hilbert space H1, and J2 acts on Hilbert space H2. We define an operator with that what we call J without a subscript as the sum of the two. Now this is really a shorthand for something much more precise. Why? Well, of course, this operator, so this acts on the joint Hilbert space of the two subsystems. So this acts on Hilbert space 1, but it's the identity on Hilbert space 2, and vice versa. So really what this, if we wanted to be ultra precise, and sometimes we do, we can write this with our tensor product notation that we discussed last semester, where in the tensor product, this acts on the first part subsystem, and this acts on the second subsystem. Okay? So that's really what that operator is. So now I ask you, is this, does this obey the properties that we expect? Is this the generator of rotations of the total angular momentum? Well, the way in which we showed, just saw that an operator J is a generator of rotations is if it satisfies the right algebra, right? And that the algebra is defined by the commutation relations. So to answer this question, we need to check the commutation relations of the components of the total angular momentum. Okay? So that's what we need to check. So what is that equal to? So there's lots of funky subscripts here, so we have to be careful. What is referring to a subsystem and what is referring to a component? Okay? Now I'm being a little sloppy in this, so you just have to be watching. So,
So here I, J are not the subscript.
that's right, these are components. So this is X, Y, or Z. Okay. So this is J1 sub I, tensor the identity, plus J2 sub I, the identity, tensor J2 sub I, commuted with J1 sub J, tensor the identity, plus J2, the identity, tensor J2. This is writing things out extremely pedantically when we rarely do this, but I'm just emphasizing some facts. The point is that we know that operators that act solely on subsystem 1 commute with any operator that acts solely on subsystem 2. Spin 1 operators commute with spin 2 operators. That's written out explicitly here, and thus we see that this is equal to the sum of the commutators acting only between operators that act on 1 or 2. Okay? And this is what?
Epsilon I, J, K, J1 sub K.
Yeah, with an imaginary I out front. And I've got, remember, these J's are gotten rid of the H bars, right? This is really the angular momentum full over H bar. So I've divided out the H bar. Okay? And similarly, this is I epsilon I J K, J2 sub K. Okay? 1 sub K. So, that means that this is equal to I epsilon I J K, J1 sub K, tensor the identity, plus the identity tensor J2 sub K, which is I epsilon I J K, the K component of the total angular momentum. Okay? Thus, indeed, this satisfies the expected commutation relations of an angular momentum. So the answer is yes. Okay? So the components of total angular momentum satisfy the commutation relations that are the generators of rotation of the total system. All right. Let me just get my notes here. Just a thing. I'm sorry. All right. Now, one thing we expect from the system is that if it's a total angular momentum, good total angular momentum vector, the square of the total vector, let's say the magnitude squared, should commute with any component. For example, the z component. Okay, let's check that. So, what is j squared? That's a shorthand for j dot j. Okay. Which is equal to j1 plus j2 dotted into j1 plus j2. Again, I'm not always going to write out the tensor products. You have to just be careful in noticing what's going on here, that this is an operator that acts only on spin 1, and this is an operator that only acts on spin 2, although the tensor product is implicit in there. That's the identity on the other subsystems. So that's equal to j1 squared plus j2 squared plus j1 dot j2 plus j2 dot j1. But since 1 and 2 operators that act on the two spins commute, we can write this as this. All right. So now the question is, does the z component of the total and momentum commute with this? Okay. So that is equal to, so now we have j squared commuting with jz is equal to j1 squared plus j2 squared plus 2j1 dot j2 commutator with jz sub j1 sub z plus j2 sub z, with all the tensor products kept in mind. Okay? So, we have to commute this with this, we have to commute this with this, and we have to commute this with that. What do we remember about that? Well, this is a spin, or an angular momentum 1, so its magnitude squared commutes with any one of the components of j1. So this commutes with j1z, right? Everyone see that? What about j2 squared? Does it commute with j1z?
Because it's on different parts.
Exactly, because this is acting on subsystem 2 and this is acting on subsystem 1, and we just said anything on subsystem 2 commutes, so that's obvious. This we don't know for sure, so we gotta stick that one. So we have this is equal to 2 j1 dot j2 commuted with j1z plus j1 dot j2 commuted with j2z. Okay, close paren. All right, so now we have to do this commutator. Okay. Yes, sir.
Can we say that these are going to be the same by symmetry?
They're not, because of the way
But
the
we
order.
have to change the 1 to a 2?
Exactly. We can't do that.
Okay.
Yep. We change the 1 to the 2. So let's do that. All right. So let's look at this guy. suggestions of how we're going to deal with that?
Component by component?
Component by component. So I write the dot product out as J1 ith component times J2 ith component. Sum over I. Okay? So this, again, I'm using the repeated index notation, right? So this is J1x times J2x, J1y, J2y, plus J1z times J2z. That's the dot product, right? Again, the one stuff commutes with the two stuff, so I could take that outside the commutator. Right? And then this is I epsilon I3k J1 sub k. Right? Because the jth index is z. So I replace that to 3. That's where we had the epsilon I jk. That's what that is. IJK. Right? So this is equal to I EZ dotted into J1 crossed into, or no, J2 crossed into J1. Okay. I goes on that side, J1 cross J2. Okay. And so as he suggested, to go through the same thing, all you have to do is flip 1 and 2. So the time you go through the same exact exercise, or you just look at it by symmetry, this is just a same thing, but now just flipping 1 and 2. This is J2 cross J1. Okay? But the cross product is antisymmetric. This is minus that. Thus, this is minus this. Thus, this is 0, as expected. So the total angular momentum vector squared, the magnitude squared, commutes with any one component of the total, which is, say, for example, Jz. However, note J1, or the total angular momentum squared, commuting with, say, just the component of one of these guys, is not 0. Similarly, the total magnitude squared commuting with J2z is not 0. It's only the sum, that is to say, the magnitude squared commuted with the total, that is 0. All right. So, what this tells us is the following very important fact. So,
just out of curiosity.
yes, please.
Are those two guys, they're both equal and opposite?
These guys are, that's what we just proved. So this is minus that, and when you add them together, they're 0, indeed. All right, so what we just have seen is the following. We have now two different bases for the total Hilbert space. one basis is the basis we've thought of. Now when we write down what we mean by a tensor product space. A tensor product space, as we discussed last semester, is the space that's spanned by all product vectors of the bases of the two subsystems, right? So, just given that, what is a basis based on just the product bases? So we know that J1, N1, the set of this, right, where N1 goes from minus J1 to plus J1 in integer steps. Is a basis for H1, right? Similarly, the set of J2, M2, remember we're fixing J1 and J2. So within the space of a fixed J1 and J2, these are the two J plus 1 standard bases. These are the standard bases. Okay? So given that, what is a basis? We have what we call the product basis. Also known as the uncoupled representation, which we will, for reasons we will emphasize in a moment. The set of all tensor products of these, okay? Which is sometimes shorthand. We won't put in the tensor product. We'll just say, you know, there's J1, M1, and then semicolon J2, M2. Okay, where M1 goes between those, bless you, and J2, and M2 goes between those. And this, there are, as we said, there are the total dimension is the product of the dimensions of the two subsystems. But we have another basis. We have the coupled represent. Well, before I say that, let me just say this basis is defined as the simultaneous eigenvectors of the magnitude squared of particle 1, the z component of particle 1, or subsystem 1, and j squared for 2, and j2 squared, j2z. So it's these guys commute with these guys. These guys commute with these. This commutes with this. And so this is a simultaneous eigenvector of, this is a complete set of mutually commuting operators. Okay. All right, but there's another basis, and that we'll call the coupled basis, or the coupled representation. So these guys will be simultaneous eigenvectors of what? Well, the total angular momentum squared and the total z component we can no longer include J1z and J2z in the set because they don't commute with the total J squared. They do commute with the total Jz, but they don't commute with the total magnitude squared. However, the magnitude squared is still a good quantum number. And that's shared, that's in both sets. Why do these guys are a set of mutually commuting operators? Well, Jz is J1z plus J2z. J2z obviously commutes with that, but J1z does as well. Similar argument holds for this, right? And the magnitude squareds all commute with one another as well. Okay? So this is a complete set of mutually commuting operators. And we denote them as follows. The total angular momentum J, the total z component m, and then in addition, if we need to denote it, J1, J2. Okay. This is a different representation. It's called the coupled representation. Okay. Now, how do we think about this? One way to think about it is geometrically. Okay? So here's a kind of geometric picture. So you remember we had this kind of, well, in 1920s language, it's called space quantization, where we said if I have a single angular momentum, suppose I have an angular momentum J1. Okay. We could think about the eigenstate J1, M1 as geometrically a vector of sorts. That is to say, there is a vector which has a definite magnitude, right? And a definite projection onto the z-axis, but an uncertain projection onto the xy axis. I won't draw them in, it's the xy plane there. Okay? So this is a vector. We can think about this loosely as we know for sure that the vector lies somewhere on this cone, but we don't know where. There's uncertainty in its x and y components. Its z component is fixed. Its magnitude is fixed. But we don't know what its x and y components are. Okay? Now, how would we add together two vectors of this sort? So if we say in the uncoupled representation, so now let's think about the total thing. In the uncoupled representation, or the uncoupled basis, the product basis, each angular momentum is specified like this, right? We have a definite magnitude and projection for each one. So I can just kind of draw it like this. There's, there's this cone. Let me come to another board so I'm not right in the bottom corner here. Let's try it over here. Does it have to be the same magnitude and the same, make those two cones different? Because they can be anything I like. So here's a picture where what I'm saying is there's a J1 vector, there's a J2 vector. Each one of them lies somewhere on this cone. And the bottom of that cone can be anywhere on this cone. And then the total angular momentum, J, is this. Okay? Now, what you see from that, I mean, if you add up any of these two vectors, so I can add up, a vector here and a vector there. That's a different vector, right? That's a different J. That's another possible one. So what you see in this case is that the total magnitude, J, is not fixed in this case. The magnitude of J is not fixed. What is fixed is its projection on the z-axis, and the individual magnitudes are fixed, and the individual magnitude on the z-axis is fixed, but the total magnitude is not fixed. Okay? If I wanted to think about the couple geometry, that's different. So in the coupled representation, the good quantum number is the total magnitude and the total projection, and then the total individual pieces. So what I have is I have a total vector J, and its magnitude along the z-axis is fixed. So it must be the case that the individual guys J1 and J2 add up to J, but their projection onto the z-axis is not fixed. What is instead fixed is their projection onto J. That way, it must, so if you think about this, this is why this is called the coupled representation. We have two guys that are kind of spinning around their joint axis. The joint axis is precessing around the z-axis, so that the total projection of the projection of the total angular momentum is fixed. The total magnitude is fixed. The magnitude of the individual vectors is fixed. But the projection of the individual vectors on the z-axis is not fixed. Okay? So this is why this is called the coupled representation, because it looks like two strongly coupled vectors that are coupled to their joint axis. And we will see this picture clearly in terms of which basis is a good basis for describing, say, eigenstates of the Hamiltonian. For example, if we, as we will see in the interaction with a magnetic field, I can have the situation where each spin is longer processing around the magnetic field independently. They're uncoupled. If the coupling of each spin to the magnetic field is much stronger, then they're coupling to one another. On the other hand, if we have a situation where the spins couple much stronger to one another than they do to the magnetic field, then they couple together to the total, and then the total processes. So we will see that in the context of, say, the Zeeman effect. All right. Now, these are two different bases, and those two different bases are complete, and thus I can express an element of one basis in terms of the superposition of the other. So, different representations. Are related. That is to say, they both form a resolution of the identity. So, for example, we can express some element of the coupled representation as a superposition just inserting our resolution of the identity. As such. So I just inserted this resolution of the identity and just played around with my notation a little bit.
By the way, you didn't mention the range of J?
I didn't.
Okay.
That was on purpose because we have to get to that. Because we don't really know that yet. So these coefficients, these expansion coefficients that relate the coupled representation and the uncoupled representation are very important in the theory of atoms and molecules. They're called Clebsch-Gordan coefficients. And use Gordan, like in the spread conversion. So these are Clebsch-Gordan coefficients. And we'll study them in some detail a little bit later in the semester. But one thing we could see, this goes to Amir's question, which is, what are the allowed values, or what is the range of values of the total angular momentum quantum numbers, J and M? Okay. We know in this case, M1 goes from minus J to plus J, and M2 goes from minus J2 to plus J2. Okay. Minus J1 to plus J1. But what about these guys? Well, that depends on what are the allowed non-zero Clebsch-Gordan coefficients. Okay? Well, as I said, we're going to study this in some detail a little bit later in the semester when we get into the formal theory of representations of SU2 in quantum mechanics, but we're just introducing it here in our first lecture. Um, so, some basic rules on, and I always will write coordinates because I'm lazy, SCG coefficients. So one rule we can write down immediately and we can easily prove is that vanishes unless the total M is the sum of M1 and M2. That is easy to prove. The other one, and I'll do that in a moment, the other one is not as easy to prove, but we will do a sort of shorthand on it. And that is that the total angular momentum J lies between J1 plus J2 and the magnitude of J1 minus J2. Okay. So let's look at these two conditions. Any suggestions on the first one, how we might prove that? I mean, let's take a look at this expansion. This is saying that this is an expansion that says this state, which has a total angular momentum J and a total projection M, is the sum or superposition of these product states, which have projections M1 and M2. Right? Well, it's easy to see from this that both of these are actually eigenstates of the total projection. Right? The total projection on the z-axis it commutes with everything. Okay? So, if I look at Jz acting on this, what do I get? So much notation here, it gets confusing.
M2.
We do, but just in terms of these quantum numbers. M, right? By definition, M is the eigenvalue of the total Jz. So this is M times that. But this operator is also, of course, this. And I can use this way of writing the total now acting on the uncoupled representation, right? This operator acts on the first component, and this operator acts on the second component, right? This operator is such that this guy is an eigenvector, so J1z acting on J1, M1 is M1, etc. Right? So as you mentioned, Keith, this is also equal to this. Because it's true for every term in this. Let me just pull it out. Okay? So, what that means is that this is true. It must be the case that the only terms that survive in the Clebsch-Gordon expansion are the ones where the total M is the sum of the individual m's. All other terms vanish. Okay? Now, one thing that it means is that there are two states that we can write down immediately. That is to say, there are two coupled representation states that we can write down immediately without knowing the Clebsch-Gordan coefficients. Okay? And they are the stretch states. Is that how you spell stretched? Yes. Thank you. So what do I mean by that? Well, let's consider the state or consider the state where we have a total momentum J and the total projection is the maximum or minimum possible projection. Of course, J1 and J2 are always there in the background. They're fixed. Okay? This state can be expressed through the Clebsch-Gordan expansion as a superposition of product states. But the only terms in the product that survive are the ones where M1 plus M2 equals N, right? I mean, sorry, equals J, right? And in this case, it must be the case that the only possible state that can be is, so I'll write them out separately. This state with maximum projection J, there's only one possible way to get that. Why is this the only state? Where it must be thus the case that J I'm writing this in a somewhat confused way, so let me start again, because there's one important point. That's like, what I'm saying is not generally true, it's only true. So let's go back. So let's consider the state, which is the product state with the maximum projection on each. Okay. That state has a total M that is equal to the sum of these guys, right? And that's the unique state that has this total M. There's no other product state that can have this total M, right? Unlike, say, M equals 0. M equals 0, there's lots of different ways you can sum M1 and M2 to get 0. But there's no way to get this total M. Therefore, this is the state which has the total projection. This is the state. This is the stretch state. Where J is J1 plus J2. So there is also a state with the minimum projection. This is unique as the only state which has this projection. These two states are states which have total J equal to the sum of J1 times J2. And M is either the maximum projection or the minimum projection. So we know that the max possible J is J1 plus J2. There's no way it could be any bigger. If it was any bigger than that, then M max would be bigger than that. And M max has to be J1 plus J2. There's no bigger M, total M than that. So, what we could then see is the following. We know that M1 is between these guys. M2 is between these guys. And M is between these guys. And now the question now is, what is the range of the possible J's? Okay. Well, the maximum possible J we can have is this. What's the minimum possible J that we can have?
Minus J1 minus J2.
Remember, J itself
Sorry,
is
minus
a positive number,
minus
right?
absolute value.
Right? It has to be the absolute value, right? Because it must be the case that J is the eigenvalue of J squared, but the minimum possible value it could be, depending on if these M values you can have, is the minimum possible J is the absolute value of the difference. We could see that, I think, if I can get my act together here, from these inequalities. Okay? So if we look at the case where we had this particular choice of M1 and M2, where let's say that M1 plus M2 is J, then that means that minus J1, J minus M2 is that, and that says also that J minus M1, never mind, that's not going to work. That's only for the Schmidt state. I'll have to think about that more carefully. Right. Right. If we have the maximum value, then M is J is J1 plus J2. So that tells me from this that minus J1, J minus J2 is between those two guys. So this says that this is J2 minus J1. So J must lie between these guys. Or the other way around, minus J2 is between J minus J1, J2, which says that J1 minus J2, J is between J1 plus J2. Okay? And since J must be a positive number, we have this rule. So the final rule we have for this is this rule. Come back to this board. This is known as the triangle inequality. It's exactly what you would expect classically. but in terms of the magnitude quantum numbers. If I have two vectors that I'm adding together, this J as a vector is between the sum magnitudes and the difference. Okay? It's true for the quantum mechanical quantum numbers as well. So going back to this sum over here, we have J goes from the smallest possible value to the biggest possible value. And for every one of those magnitudes, M has a projection that goes from minus J to J. Now, it is a challenge for you to show that the dimension of the Hilbert space is in fact the same for both of these cases. That is to say, if I do this sum, the total number of vectors that I get here should be the product of 2j plus 1 times 2j plus 2. All right, I want to finish, though, this lecture in our last 7 minutes, because I have always an extra 5. An example. So let's consider two spin 1/2 particles. Okay? And I want to look at the total spin. So we have our two representations. We have the uncoupled representation, which are the simultaneous eigenstates of S1 squared and S1 sub z and S2 squared and S2 sub z, right? Each one of these are the states Sm sub s, but in those are the two states spin up and spin down. When we are fixing the total spin of each particle, we don't typically write that quantum number, right? So the uncoupled representation in this case would be up, 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 down, down, up, and down, down. Of course, this is a shorthand for 1/2, 1/2, tensor 1/2, 1/2, right? But we're not going to write all those quantum numbers out. This is spin up, and this is spin up, and then I have it spin down. Okay. That's the uncoupled representation. The coupled representation are the simultaneous eigenstates of the total S squared, the total SZ, the total S1 squared, and the total S2 squared. This is automatic. Everything in our Hilbert space is an eigenstate of that, because they all have a definite spin. Spin 1/2 for particle 1 and particle 2. What about these states? Are they eigenstates of these operators? They can't be eigenstates of both, but they are eigenstates of this, right? Because this actually can sit in both sets. So let's quickly do that. So SZ acting on up, up right? Of course, that's a shorthand for S1Z plus S2Z acting on up. S1 acting on a state gives me a half. S2 acting on the state gives me n equals a half, so this is that, right? It's a half plus a half. What is this? Zero, right? This is sum of the m's. In this case, they're opposite. It's 0. Similarly, for this acting on down, up. And for down, down,
-1.
-1. Thank you. Times the state. So in this basis, SZ, the total SZ is diagonal. The total SZ is 1, 0, 0, -1 in the basis. That is the uncoupled representation, and zeros everywhere else. Okay? But what about S squared? Well, that's the tricky part. How are we going to do that? Well, so S squared will not be diagonal in this. So to find the coupled representation, a brute force way to do it is just to express these operators, in particular this operator, in the uncoupled representation, and then diagonalize the matrix. The eigenstates are then the coupled eigenstates. So let's do it, if you'll bear with me. S squared is S1 squared plus S2 squared plus 2 S1 dot S2. Okay? This now has to act on the states. We want to see how it acts on each one of these states to find the matrix representation. Okay? Of course, this is fit. This is S times S plus 1 times the identity, right? And that's 3/4. What about this? How do we deal with this? Well, this is the x component, the y component, and the z component. Again, this is really the tensor product. Okay, so how are we going to act these operators on the uncoupled representation? Well, we know how this acts, right? Because this is an eigenvector. I mean, the uncoupled states are eigenstates with eigenvalue plus minus 1. So I think we're going to have to finish this up in the last, in the next bit of the class, next lecture. But it's a trivial business, and we'll find, in fact, that there are 3 states. I mean, that there are 2 kinds of states, singlets and triplets. And we'll finish this up next time. All right. There will be homework. So, look at that.